Okay. Yeah. First, let me thank that I have the opportunity to talk, to give a talk here at this interesting symposium, and I will talk about microchip technology applied to the assessment of water quality. I think in the morning session, several talks already addressed the importance that microorganisms in fresh water has to be identified, and I think everybody knows bacteria, cyanobacteria, virus, protozoan, cyanotoxins, diatoms are the most interesting species here. And what we actually try to do within the microAqua consortium is to develop microarray, to apply the microarray technology for the identification of microorganisms. So in my talk I will give you a little more background ideas of the microAqua project, and then as a kind of introduction, then I will move to some basics of microarray technology, and then at the end I will go back what we really did within the microAqua project with the microarrays. Okay, so as I have mentioned, the idea was within the microAqua project to coordinate activities that already have been around in Europe, in working with the freshwater samples, to integrate it and then actually to develop, in the best case, a kind of universal microarray for detecting of some microorganism. Why is that so important? There are more than 100 types of pathogens, bacteria, viruses, protozoa, actually that can be found in contaminated water. There are some drastic cases like waterborne diseases, but also here in the middle of Europe, sometimes we have a bloom of cyanobacteria, for example, and that can be can be a big problem. So that, for example, happened in the Baltic Sea. What you see on the map is the Baltic Sea. This is here Germany, that's Poland, that's Sweden, that's Finland. And you see as the image from the NASA, has been taken by the NASA, that there was a very strong bloom a couple of years ago. So, and then actually action is needed and the species have to be identified. And within the microAqua consortium, there was a goal to develop a microarray, step by step of course, for certain bacteria, cyanobacteria, protozoa, and diatom species. Okay, this is of course a lot of work and it's much more than one partner could do. Therefore, okay, here's it summarized again. The idea was to design specific probes that allow the identification of the microorganism, and then to use a microarray technology. So that means it should be, the idea was to do to use a classical slide format to do the printing of these arrays, and then finally by obtaining such images that you can identify certain species, and also to allow at least to a certain degree a quantification of the microorganism. And yeah, this, what I have mentioned before, this is too much just for one partner, therefore there was a big consortium of the FP7 program with different partners all around Europe. And actually here are the 12 partners are listed that have been working within the microAqua project. So it really ranges from Turkey, Bulgaria, Ireland, Italy, France, Spain, Germany, and UK. So, and now we are in the final stage of this project, and therefore also in the afternoon session you will find a couple of talks that are related to the microAqua project. Okay, what actually maybe first should explain what is a microarray. So array-based analytics, the main thing is that you are working with, you have a substrate that carries different spots, and the spots have an average diameter maybe of 100 micrometer. So in each spot there can be a capture molecule, can be immobilized. This can be done for DNA, for glycans, for proteins, or even cells. And the capture molecules can interact with some components from your sample, so with the analytes. So for example, in case of DNA or oligonucleotide arrays, then you would see a specific hybridization, but only with the analyte molecules where the corresponding complementary oligo strands have been immobilized in a single spot. So, and that can be done actually on classical slides. This was the origin of the array technology, but this has also been switched to microplate format, or you can, for example, if you want to do some apeirometric detection, whatever, then you can apply this technology also for biosensors. So, and then the classical way of detection would be a fluorescence detection or the colorimetric detection. So, in this way, you can investigate a population of different organisms, and if you have this population, that means you also have an assembly of different identities. So, and based on the DNA identities, then you can create for each species a different set, a specific set of probes, where you can then, by using such an array, then you can identify the species that are in your environmental sample. Okay, in special, what we did here in the MicroArca project, we applied RNA microarrays. So that means you have a substrate. This always has to be chemically modified in some way to attach the oligonucleotides. And then from the environmental samples, the RNA has been isolated, it has been labeled, and then you can observe the hybridization. And what you get actually at the last step is a fluorescence scanner image, and then you have printed multiple spots. Also, you have spots here where you don't see any signals, and from, or here you see some signals show up, so other signals don't show up, and then from the signals that light up, you can conclude which species are in your environmental sample. Okay, I would give you some more explanation. That could be a very long lecture, but maybe it's something what is really important. For example, the array technology is very often used for miniaturization of classical DNA-based or antibody antigen tests. But you have to remember that to get a good performing microarray, you will have to optimize different parameters. So first is the selection of the substrate of the slide, what kind of substrate you use as a slide or membrane or microplate, whatever. Then you have to make sure that you can print very nicely formed spots. And then is the main difference. Classical assays, they work in solution. If you operate with tiny droplets, that means after spotting tiny droplets, the solvent is evaporating very quickly, so you get a kind of dried state. And at the same time, you still want to make sure that many of your capture molecules are efficiently immobilized. Okay, so there are some general surfaces that can be applied. So the classical case is that you would go to Schott Bacterium and you would buy some slides for DNA application, for example. And the classical standard slides are based on self-assembled monolayers or functionalized glass substrates. There are also 3D layers available, or even more. The main difference is the kind of networks that you have here and the thickness of these layers, where you can use these layers especially for protein applications, where the maintenance of bioactivity of the capture antibodies is very important. Okay, and if you, for example, start with such a project and you start with a classical slide format, but maybe you consider, okay, I would like to have a little more fancy and maybe also more cost efficient to switch to polymers or maybe even to biosensors, you have to make sure that you consider that at the very early stage of such a project, because technologies of surface functionalization like silanization, plasma, photopolymerization, or functionalization of gold substrates are really quite different. Okay, and the final thing then is how to get such a spotlet. This technology is around about since, I think, 15, 20 years. There are different procedures how you can print these microarrays, like what you have, a kind of sliced pin technology, microstamping, photolithography is a different principle, or electrospraying. If you want to do something in your own lab, then it's probably recommended to buy a printing system. So there are two main groups, a contact printing system and non-contact printing. And what we have done in our companies, actually, we have focused on non-contact drop-on-demand printing technology. So you generate tiny droplets, about 100 to 500 picoliter large, and then you print these arrays. You can image them by head camera, CCD camera, or by fluorescence scanning, whatever. So what is very important, if you don't optimize the single components of such a microarray, you get some spots, but you have a very low degree of reproducibility, and then the final results would be very disappointing. Okay, I would like to come back to the microAqua project. So to the general workflow. So the first steps, what we have done is, has been the design of the oligonucleotide probes. And then there was also a decision which kind of surface, which kind of substrate we would use, and the attachment chemistry. Then you have to apply some printing and immobilization procedures. And finally, if you have done that with reference samples, you can undergo the validation of these arrays. During the entire time of the project, there has been already a collection of field samples has been performed. And this is just the first step. Then you have to go to the next step. This is filtration of the samples to collect the microorganism. Then you have the storage step of these filters, and then finally RNA extraction, hybridization, fluorescence scanning, and data analysis. So this is just the entire workflow. And just to give an overview, so samples have been collected by the different partner organizations, so all over Europe. So altogether, I think approximately 250 samples have been collected during the 2-year campaign. And so then the next step was, so samples have been, 50 liter of each field sample have been collected. So, and then the next challenge was how to get out all the microorganisms. So we have applied a large volume sample concentration filtration procedure, where you get a kind of enrichment of the microorganism. And then this is step 1. And then step 2 was the microorganism recovery from a so-called backflush solution. And then you still want to distinguish, you want to collect the different microorganisms by sequential ultrafiltration. So there have been 8 different filtration steps have been applied. So in the final steps then, because the arrays have still not been ready at the beginning of the project, so we have to store these samples without destroying the RNA. So these samples have been stored in tree reagent at -80 degrees. Okay, so then we have developed different generation of these microarrays. At the moment we're operating with generation 3 microarrays. It was also a time when we started to analyze the field samples. And then the next step is to do pooling of the filter samples. Then you have to apply the protocols for the RNA extraction. Then you have to apply protocols for RNA purification. That is actually pretty challenging, because if it's not pure enough, then labeling later on will not work, and finally you can't do the hybridization. And the samples that we're dealing with are really field samples, so there are some contaminations inside, and you can apply UV-based measures or also running electropherograms, but sometimes you don't get a full indication what's going on with these samples, and then you just wonder what's the reason that the labeling with the fluorescent dye doesn't work properly, so you have to go back to improve purification, for example. Okay, so same time, especially for the generation 3, we have then printed the microarrays, also the oligonucleotide microarrays, and here we have printed 240 probes and 8 replicates. So this is just a scheme of such a microarray, and then after hybridization you obtain such a fluorescence scanner image where you see, again, you can find here the different quadrants, and there are always some landing lights that help you to identify the right position of these microarrays. So this is actually what you want to get. So then the next part of the work is starting, because you see there are many spots, and you have to do a data analysis. So first, of course, you will do a kind of quality control. In each case, we have done at least 2 hybridizations for each field sample, so you can compare if you get exactly the same result. One method to do that is an application of so-called scatter plots. So the hybridization from one sample, as the first and second hybridization, are just compared in their intensity, and if And if all data would be on a straight line, then everything would be great. But of course, this kind of real microarrays, and there are some outliers. Okay, but here, especially the controls, you see they are nearly on a straight line, so the quality of these arrays has been good, and also the intensities that we have observed. So in principle, that's working pretty well. And yeah, the next step then from that is that you can prove the existence, you can check the existence of the specific probes that can be assigned to one microorganism over certain time periods, and then even one step more, that you can start with quantification of the microorganism. This is just actually the kind of, at this point I will stop with my talk, because the next talk that will be given by Delphine, she will focus much more on all these validation experiments that we have done, and also then give you much more explanation about how you can prove that a microorganism really has been in your sample, and also how you can do this calibration work to get then certain cell numbers. So I don't have prepared really a summary, so I think this symposium is called Small Solutions for Big Water-Related Problems. So a summary, I think it's small spots for big water-related problems that will cover that. And before I stop, I would just let you know that I'm from Scienion. This is a small company based in Berlin. It's a spin-off of Max Planck Institute of Molecular Genetics, so we already exist for approximately 14 years. There's also a small company in the US now. And yeah, so we do all kind of array-based analytics. So actually what we do is that we have a technological platform. If you want to miniaturize your tests, then you can contact us, and we probably can give you some support. You can also buy consumables and equipment, whatever. Okay, good. Yeah, thank you very much for your attention.